My pleasure to introduce our next speaker, Mahur Joglekar from University of Maryland in College Park, who's going to speak to us about periodic windows within Windows within Windows.
Hi, so I'm going to talk about periodic windows within Windows, or nested periodic windows and the robustness of attracting orbits in the presence of disturbance. So, as many of you might have seen, this is the equation of the force damped pendulum, where this is the forcing term and this is the damping term. And these two diagrams represent the basins of attraction of the force damped pendulum for two different values of the parameter rho. So for rho is 2.45, the system has a chaotic attractor, which is denoted by this green region. The x-axis is the variable x, the y-axis is x prime. So for rho is 2.45, the system has a chaotic attractor, and the blue region around it denotes the basin of attraction of the chaotic attractor. Now if you bring about a small change in rho from 2.45 to 2.55, then the system behavior is no longer chaotic but becomes periodic. So if you look at this diagram, these points over here show periodic attractors, and the regions around them, this gray region, the blue region, and the pink region are the basins of attraction of the periodic attractors. So attracting orbits in the system can be really dependent on small changes in parameter values, which is why it's important to study the robustness of attracting orbits. So again, this video denotes how the basins of attraction of the force damped pendulum vary with changes in parameter. So here you can see a blue region, which is the basin of attraction of a periodic attractor. The periodic attractor is not shown in this. And the pink region, which is the basin of attraction of another periodic attractor. Now as the parameter rho increases, the basins evolve. And for this value of the parameter rho, there is a chaotic attractor and no periodic attractors. As you increase the parameter further, the chaotic attractor evolves, and again there are periodic attractors and so on.
Put it on view and then full screen mode.
Okay, so to study the robustness of attracting orbits, let me define what I call an epsilon at a certain point. A point x comma c, where x is the state variable, c is the parameter, is called an epsilon at a certain point if it lies in the basin of attraction of a periodic attractor, but is within epsilon of chaos. So in other words, if you bring about a small change in x comma c to x prime c prime, a change of magnitude less than epsilon, then the behavior changes from periodic behavior to chaotic behavior. Now the questions that I am interested in addressing is what fraction of the space consists of epsilon at certain points, and where are the epsilon at certain points most likely to lie. So if I pick a value of epsilon and randomly pick an epsilon at certain point, then where am I most likely to see this epsilon at certain point? Now in high-dimensional systems like the force damped pendulum, addressing this question becomes difficult because it's very difficult to predict the asymptotic behavior of the system, since a point can lie in the basin of attraction of a periodic attractor but can take a really long time to converge. So we look at the case of the one-dimensional quadratic map, which is a simple map but shows interesting behavior, and this map has an interesting property that if you start from x is equal to 0, and for that value of c, you have a periodic attracting orbit. The trajectory converges to the orbit really quickly. So this is the bifurcation diagram of the quadratic map. The parameter range that we are interested in is minus 0.25 to 2, where it shows a lot of interesting behavior. This point is the Feigenbaum point where chaos occurs for the first time. The bifurcation diagram has these tiny regions which are called periodic windows. So a periodic window is a region in parameter space that starts with a periodic attracting orbit and that undergoes a sequence of period doubling bifurcations till you get chaos. So if you zoom in on this part of the bifurcation diagram, you get this region which is a period 3 window because it starts with an attracting period 3 orbit, and as you increase the parameter, there is a period doubling from period 3 to period 6, and there are repeated period doublings till you get chaos when there is a 3-piece chaotic attractor, and as C increases further, the 3 pieces merge to form a single piece chaotic attractor. So periodic windows display some interesting properties. First of all, there are infinitely many periodic windows. So as you look at higher and higher periods, there's an exponential growth in the number of periodic windows. The periodic windows are dense in parameter space. So if you pick any value of C, you can find a periodic window arbitrarily close to that value of C. And they display a fractal structure. So if you look at any window, a primary window, which is any window that you can see in this bifurcation diagram, and you zoom in on the primary window, then you can see these tiny regions which are called secondary windows. And if you zoom in on the secondary windows, you can see similar tiny regions called tertiary windows and so on. And if you magnify this region, then you get a bifurcation diagram which is almost similar to the original bifurcation diagram. So that's what I mean by a fractal structure. Now I have already talked about what an epsilon uncertain C value is, and in context of the quadratic map, an epsilon uncertain C value is any C value which, when perturbed by an amount epsilon, the behavior changes from periodic to chaotic. So if I pick a C value here and reduce it by epsilon, then this C value is periodic, but this C value is chaotic. So that C value is epsilon uncertain. Similarly, a C value here is epsilon uncertain because if I increase it by epsilon, then the behavior changes from periodic to chaotic. On the other hand, if I pick a C value somewhere in between, then it's not epsilon uncertain because on perturbing it by epsilon, the periodic behavior persists. So the fraction of epsilon uncertain C values in the window depend on how large the window is. If the periodic window is really small, then any randomly chosen C value in the window will be epsilon uncertain. However, if the periodic window is large, then only the values close to the edges of the window are epsilon uncertain. So there was a numerical experiment done in this paper in which they computed the fraction of epsilon uncertain C values as a function of epsilon. So they chose various values of epsilon, randomly picked values of C, and decided whether or not they were epsilon uncertain by computing the Lyapunov exponents. And this diagram shows the fraction of epsilon uncertain C values as a function of epsilon. What they got was a graph of slope 0.41, which indicates that the fraction of epsilon uncertain C values varies as epsilon to the 0.41. So if you pick an epsilon 10 to the minus 7, then that corresponds to y is 10 to the minus 3. So 1 out of 1000 randomly chosen C values turn out to be epsilon uncertain. So in order to study the fraction of epsilon uncertain C values, we decided to look at the distribution of the widths of primary windows, and we use kneading theory to determine the sequence in which the Milner-Thurston kneading theory to determine the sequence in which various primary windows appear as the parameter of the system is increased. So as I have already shown, this is a picture of a period 3 window, and the width of the window is defined as the parameter difference between the crisis point, that is this point, where the 3 chaotic attractors merge to form a single piece chaotic attractor, and this point, which is the saddle node point, where the period 3 attracting orbit emerges. So this distance is referred to as the width of the window. And what we did was, as I already said, there are infinitely many windows, and as the periods of the windows increase, there's an exponential growth in the number of windows. So it's not possible to compute the widths of all the windows. So we fix a maximum period and we look at the windows of period smaller than or equal to that period. And we fix the period. So we looked at maximum periods 13, 15, 17 and so on till 25. Since there were a huge number of windows, approximately 1.4 million windows, we used cluster computation with 100 processors in quadruple precision, and this graph shows n of epsilon, which is the number of primary windows with width greater than epsilon as a function of epsilon. What we observed was that as we chose a higher and higher value of maximum period, this graph seemed to be closer and closer to a straight line with slope minus 0.51. So what we believed was that if we looked at all the primary windows of periods till infinity, then the relation we would get between the number of primary windows with width exceeding epsilon as a function of epsilon would be this, where 0.51 is the scaling exponent because it gives an idea of the scaling of primary window widths. So this is the straight line with slope minus 0.51. The original question that we were interested in addressing was the question of the fraction of an epsilon uncertainty values. So how does the scaling exponent relate to the fraction of epsilon uncertainty values? As I already mentioned, depending on the size of the window governs what fraction of the epsilon uncertainty values in the, what fraction of the window is epsilon uncertain. So a relationship can be established between the fraction of epsilon uncertainty values in primary windows and the scaling exponent, which gives this number 0.49. What this indicates is that if we repeat this numerical experiment and we look only at those C values that are epsilon uncertain but lie in primary windows, then we expect to get a graph of slope 0.49 instead of 0.41. So we did repeat this experiment, and as expected we got a graph of slope 0.49. And this is interesting because it indicates that as epsilon takes smaller and smaller values, the distance between these two lines goes on increasing. So as epsilon tends to 0, a randomly chosen C value that is epsilon uncertain does not lie in a primary window but in a higher order window. So as epsilon goes to 0, most of the epsilon uncertain C values lie in higher order windows. Now this is something that we got through numerical simulations, and we wanted to see if we could establish this through the primary window width scaling that we had, which gave a scaling exponent of 0.51. So like I said, periodic windows display a fractal structure in which windows of various orders are almost self-similar to one another. So we assumed exact self-similarity of periodic windows, which means that if you look at a primary window and if you zoom in on the bifurcation diagram, then if you zoom in on any region of the bifurcation diagram, you get a bifurcation diagram similar to the original bifurcation diagram. So assuming exact self-similarity and using the scaling relation we had for primary windows, we arrived at a scaling relation for kth order windows where k can take any positive integer value. This relation was a polynomial in log of 1 over epsilon, and based on this, through a series of lemmas, we arrived at the following theorem. What this theorem says is that if an epsilon uncertain point is chosen randomly, then say this point lies in a window of order r, then as epsilon goes to 0, r goes to infinity with probability 1. Or in other words, as epsilon takes small values, most of the randomly chosen epsilon uncertain points do not lie in primary windows or secondary windows, but in nth order windows where n takes a very large value. And as epsilon takes smaller and smaller values, n takes larger and larger values. So in other words, randomly chosen epsilon uncertain points lie in windows within windows within windows n times where n is very large. And this is the theorem. So the lemmas that were used were based on the fact that assuming self-similarity, it can be proved that for any value of order k, an epsilon can be chosen small enough so that the probability of a randomly chosen epsilon uncertain point lying in a k plus 1th order window can be made arbitrarily large as compared to the probability of it lying in a kth order window. So that's my main result. And I would like to thank my advisor, Jim York, and Dr. Rod for the suggestions. Thank you.
Okay, we've got a lot of time, so comments or questions for Maddie?
So So right now we've shown this for the quadratic map case. We expect it to hold even in higher dimensional systems, but we're still working on it.
Could you please tell us?
Would something like this maybe hold for all of these single maximum continuous
We think
maps?
so, yeah.
Could you please tell us how the problem originated? Because I did not understand that.
Oh, okay.
Mhm.
So,
Oh,
yeah, so if, say a parameter value is chosen and or a point x comma c is chosen, where x is the state variable, c is the parameter, and it's epsilon uncertain, which means that it's not robust for epsilon disturbance. Then the question is where in the parameter space or where in the state space are we most likely to find this terms?
So, is this related to complex function theory? Because I've seen similar.
We have not looked at the relation.
When you were varying the parameter r and going from some periodic attractors to chaotic attractors, so as you move up, the boundaries between the different attractors seem to be getting more and more highly intermeshed. Do they become fractal?
Yes, they do. So the reason being that there are infinitely many windows. Now windows are regions in parameter space that show attracting periodic behavior that eventually becomes chaotic. And these windows do display a fractal structure. So if you zoom in on any of the primary window, then look at this side. So this is a primary window. So this is this region zoomed in on. Now this diagram, this bifurcation diagram inside the primary window is very similar to this original bifurcation diagram. So it shows the same order of same order in which windows appear.
Yeah.
So and there is an exponential growth in the number of period T windows as P increases. So the windows become closer and closer to each other.
I think of your very first picture that you had of the movie.
Right. So the very first picture was for the four-stamp pendulum. That is.
Yeah. So if I look at that, the boundaries seem to get very, very complicated.
Oh yes, this.
Between the two, the different attractors, and I'm wondering whether, if, for example, I moved rho from 2.55 down to 2.45, as I get there, does in some sense, I would have the sense that within some small neighborhood of every point, you have different basins of attraction. In other words, there's no interior to those.
At some point, there would not be so the measure of the basin would go to 0.
Yeah.
Yes.
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 Okay.
Yes, that's it. Yeah.
I saw a reference to fat fractal dimension.
Yes. So the fat fractal dimension paper is which does this numerical simulation in which they compute the fraction of epsilon in certain C values as a function of epsilon. But they look at every C value which is epsilon uncertain regardless of the order of the window it is in.
Yeah.